Hello, and welcome to the Satellite Image Deep Learning Podcast. I'm Robin Cole, and it's my pleasure to present another technically focused episode in the series. In this episode, I caught up with Inon Sharony to learn about the fascinating world of machine learning with SAR imagery. The unique attributes of SAR imagery, such as its intensity, phase, and polarization, provide rich information for deep learning models to learn features from. We discussed the innovative applications ASTERRA is developing and covered the nuances of performing machine learning with SAR imagery. Coming from a background with limited SAR experience, this conversation was incredibly enlightening. I hope you enjoyed this episode. Hi, Inon. Welcome to the show. Why don't you begin by telling us where you work and what you do?
Hi, Robin. Thanks for having me. So, my name is Inon Sharony. I work at ASTERRA, which is a company. We have several offices. Our main office is in Israel, in Tel Aviv, and we have offices in the US, San Diego, in London, UK, and also in Japan, China, different locations. What we do is we do SAR analytics. So we study SAR imagery for different applications, and yeah.
Cool. Why don't we begin by saying what's special about SAR then?
Okay, so SAR for people who don't know is a remote sensing technology which is in the overall radio frequency spectrum is somewhere in the radio frequency. So it's somewhere between infrared and the longer range radio. It's about, I'd say, tens of centimeters in wavelength, which translates to about a gigahertz to 10 thereabouts in terms of frequency. What's special about this wavelength is, well, several things. First of all, it is basically the atmosphere is transparent at this frequency, meaning that the water vapor in the atmosphere does not interfere. And that basically means that what we use is capable of operating through clouds in any weather conditions, pretty much. There's passive sensors at this frequency and active, and SAR is active in that it transmits as well as receives its own signal. So we're not dependent on external illumination as opposed to usual optical imagery. Yeah, so those are the main, I would say, two strengths. A part of that, one of the things that works to our advantage is that while the water vapor in the atmosphere is kind of transparent to us, the water in the ground or water moisture in the ground isn't. So
Hmm.
at the bands of frequencies that we're talking about, and they're named in letters, so you have K, X, C, S, P, L, which is what we use. We are very sensitive to the electromagnetic permeability of water. Sorry, permittivity. So that means that we are able to discern not only quantities of water in the ground, but we're also able to discern the salinity content of that water. So we'd be able to differentiate between rainwater, potable water, wastewater, anything like that. And yeah, and there's, the usual stuff that you can do with electromagnetic sensors. So we can polarize the signal that we send out and polarize the signal that we get back, or filter them by polarization and kind of decompose the signal according to that. We get additional information.
Hmm.
And we can also play around with the phase. So if we judge the signal coming back as a complex value, it has a backscatter amplitude or intensity, and also we can check how much the phase has changed. And that gives us two things. First of all, it's yet another degree of freedom, another source of information about the structure of the target that we interrogated, as well as to perform interferometry, which
Right.
gives us centimeter resolution in the vertical axis, let's say.
Hmm. So really strong properties for interrogating the ground and understanding both what's happening inside the ground, moisture, but also small changes to the level of the ground. That's a really interesting capability.
Yeah.
Fantastic. So, you've mentioned some of the potential uses. What are the particular applications that you've been working on at ASTERRA?
So, as I started mentioning, we are mostly interested in things that are, let's say, water content in the ground, whether that is for detecting water where water shouldn't be. So, as a general statement, you could say that we are targeting a lot of critical infrastructures. So that could be, let's say, water pipes or water utilities that have their own infrastructure of water pipes, and those may leak. Um, you'd be surprised how much of a problem that is with an industry where, basically using aging, let's call them that, aging infrastructure and not necessarily capable of replacing it at the rate that it's breaking down. So we're helping that industry in recovering the water that's lost and they don't get
Right.
revenue for, which is the non-revenue water. Um, so that's one thing. And another thing is, let's say, transportation infrastructure, mining, dams, all these places where you don't want to see excess soil moisture because that basically will possibly lead to, I would say, about 80% of all earthworks projects that go wrong probably have that water element or factor that contributed.
Hmm.
So that's another product line that we're dealing with. We have a few more. We had a spin-off recently where we were able to detect mineral content beneath the surface, and that was, for example, lithium, which is a very important element this day and age.
Right. Really interesting. So many of these will be, I guess, typical measurements. Where does machine learning fit in?
Okay, so as I mentioned in the beginning, the SAR image or data in general is quite complex. Um, so we do have all these degrees of freedom, the polarization and the phase and so on, which means it's not like an RGB image, or it's more like you would see in, I guess, what you're used to with multiband or sorry, multispectral, or possibly even more than that. So we have a high dimensionality input that we need to make sense of. Another challenge we have is that because we're dealing with a wavelength that's very different from visible light, we don't have the benefit of being able to manually label or annotate our data. So we're working in an area where machine learning is a very important tool, both in making sense of the data that we have and also in completing the full cycle of building the application. Um, so yeah, we use it for anything between, making sure that the data that we get is similar to in terms of data distribution to previous images to rule out any anomalies, and onwards to pre-processing it and trying to extract features, which are, as I mentioned, probably going to be deep features for us to be for them to be useful.
Hmm.
Um, And then we have, the regular supervised or unsupervised or semi-supervised, self-supervised. We have the entire array that mostly depends on the kind of labels that we have for supervision. In some cases, those are more forthcoming, but in our case, usually they're not. So we have to be creative about it.
Hmm. Does that mean that you have to have models that identify anomalies and then somebody reviews if you think it could have been a water event or something else?
So that's a good question. So for the case of let's say the basic product that we have, which is the water leak detection, in that case we are building on existing experience where known leaks were identified in field work, which is expensive and extensive, and you need to have good design partners for that. So we did have a kernel of ground truth samples that we could start and build from. So in that case, we started with the basic vanilla supervised convolutional neural networks in those cases, and those worked out good, well. So we went on to, use that system more and more, and now it's basically the system that we use in production. For other cases, we did not have as much luck with getting ground truth data, whether it's from, so, I could give the extreme example of looking for something like lithium, which is not, well, in recent years it has boomed, but there has not been a whole lot of existing work on where lithium would be found in substantial quantities. So in those cases, we did have to resort to things like self-supervised and things like that. And then, at the other end of that spectrum, you also have the anomaly detection and unsupervised, where by that I'm talking about things that are really outliers, like defective imagery detection, for which we do have known failure modes of SAR or generally of any satellite data product, but yeah, we also want to catch the unknown unknowns. So in that case, you're just comparing any new example to the existing the distribution of existing samples, and trying to flag anything that somebody will need to look at
Hmm.
discriminatively.
Right. So very scarce on the actual annotated data, various techniques for identifying potentially interesting
Well,
imagery.
yeah, I think in general that's a statement that's broadly made about remote sensing Earth observation as a whole, is that we do have very large amounts of data coming in, but not necessarily as much annotation or labeled examples thereof. So I mean, for people starting off in the field, they will go to, let's say, some Kaggle competition or some other challenge that was set forth, and these are really good primers to get a, kind of a foothold on what it would mean to work with this or other kind of imagery. But in the real world, you're not always presented with pristine and well-ordered data sets, and they're not always on the scale that you would want to train, let's say, a vision transformer from scratch.
Mhm.
So those are the real-world challenges we have.
Right. Okay. And I guess what's the state of the art in SAR at the moment? I'm very familiar with optical sensors, but less so with SAR. I'd love to hear about that.
Yeah, so I think for the reasons I mentioned, as well as the, I guess the preference of the different satellite operators towards the visible and IR sensors, that there are not as much SAR data available. There's of course Sentinel-1 from ESA, which is C-band and dual pole. We use quadruple polarized, so that's even more information in that image, but so the state of the art is based on, let's say, Sentinel-1 imagery. It's usually based on, kinds of cross-modality things that people play with, like trying to remove clouds in Sentinel-2 images using a Sentinel-1 image, which corresponds somehow. Um, the challenge is there being first and foremost getting the two images co-registered. So you're looking at the same thing. But I think what most people are playing around with, as I mentioned, are things like self-supervised learning, using different engineered features from, in our case, the polarimetric aspects of SAR. So those would be things like the decoherence metrics or things of that nature. So you're using some kind of a physical first principles understanding for at least the initial features you want to play around with. But more cases than not, those are piped into the network alongside the raw inputs, and we just leave it to the deep learning model to figure out how it wants to play around with those things and get the most value.
Hmm. Yeah, I feel like there's probably ample room for domain expertise in the pre-processing and the feature engineering side. Is the data
It
also
will it
amenable
will
to sorry, is it also amenable to like classical techniques like random forest?
Yeah, so we for example, we did play around with that. I think for the most part nowadays, for what you would expect from state of the art with any kind of computer vision, the classical or less deep methods are either going out of style, or as we found out ourselves by trying both, you end up looking for deeper features because the SAR input, as I said, is it's complex both in the sense that it has different kinds of noise distributions, as well as, well, we're looking for physical phenomena which are just not as simple as, is it a cat or dog, you know? I mean, if I look at an image and try to judge of, whether it's a field or a forest, that could be an easier problem to solve than, even without very deep understanding of how to work with imagery, as opposed to things like, is there a water pipe burst underground? So we do need those deeper features, I think. I mean, that's what our experience has shown, and therefore, yeah, our go-to tool is deep learning, and we try to use, as I mentioned, the classical feature and engineering techniques as something to get us that, first step closer to the end goal. But yeah, it will probably not get us all the way there.
Cool. In terms of the actual architectures you're using, are they architectures I would be familiar with, like the UNet, or are there particular
Yeah,
architectures?
yeah. So we're not shy about using anything. So we will reach for the classics, the convnets and the UNet, if we want to do semantic segmentation and so on. So those are usually what we would try to get our baseline on. And then we will try different, well, stuff we see in papers usually, or different thoughts that people have in the team of, how to combine features, how to try to perform a multi-stepped training procedure, as I mentioned with SSL, for instance. Usually, we have to go as far as that in order to get the level of detection performance we want to achieve. But yeah, even the reference or baseline architectures, like just a very basic convolutional neural network, will probably already outperform classical algorithms in the field.
hmm Fantastic. Thanks so much for the technical dive. I'm interested a bit in the product side as well. How does the product look? Is it just a map? Is it images? Is it alerts?
Right. So ASTERRA's product is basically a software as a service, a SaaS product. So we have an online application which is known as EO Discover, EO standing for Earth Observation. On that platform, we serve all our solutions, be they the leak detection or recover product or solution, as we call it, earthworks, and so on. And yeah, the idea is to have everything located in one place for our customers to choose and be able to get the solutions they need. Um, there is always that extra level of, as you say, the presentation layer, or how you deliver the insights to the customer. These are extremely important for us because, yeah, we have the level of basic algorithms and trying to process the data and get it to a level that is, we think, is insightful. But we have to remember that our customers are not necessarily data scientists, and this is true for everything you do. So we're looking for that specific business value that we can present to the customer and show them what they need to know. Now, my aim is to try to get the model as end to end as possible. So if we know the business metric that we're trying to hit, we'll try to train the model and optimize for that directly. Because deep learning models will do whatever it takes to optimize for that, and we don't always know how to build a model that will go halfway and then manually post process the other half of the way. So we're trying to do it all in one shot, and
hmm
yeah, it's been working out for us so far.
Yeah, I'm interested a bit about those business metrics. So there must be some practicalities, like you're alerting on a leak, but a leak can start small and grow. How do you decide
Yeah.
when a leak is significant? Something as basic as that.
So, as I mentioned in the beginning, the problem we have, I mean, not we have, but our customers have with their infrastructure is that it's very old and it's not maintained as much as they would want. Um, which basically means that the problem space is ripe for disruption, right? So they may have a leak that's been going for weeks or months, and they won't even know about it. So in many cases where they're with weeks old imagery, and it's highly relevant still. So that's on one hand. What was the question again? I want to make sure I
Oh,
hit
about
the.
turning sort of model outputs into business metrics
Okay.
or business identifiers.
Yeah. So as I mentioned a bit regarding the previous question, so when we train a binary classifier, we can say, is this a leak or not, and try to optimize for accuracy. But for the business aspect, that would be suboptimal because we are not treating, let's call them missed leaks, where we are like false negatives, the same with the same weight as we would a false positive. It kind of depends also on the context of the customer. Certain places in the world, if you lose water, it's not as expensive as in other places. In certain places, the cost of going out looking for and repairing a leak would be more expensive. So they're a bit more concerned about their precision, not just the recall. So it's always about balancing a composite of KPIs. Yeah, but we can always kind of weight our samples, or make some kind of customize somehow our loss function, to try to get it as much as possible aligned with the business metrics that we're interested in optimizing.
Mhm. That's really a fascinating insight. Thanks for sharing that. So does ASTERRA publish their techniques? Do you publish in conferences or?
Yeah, so one thing we always do to try to protect our intellectual property is file patents. So the company has about, I think, 15 patents. I'm not sure I'm even up to date on that. Um, we usually would send people to present in conferences that are broadly about space tech, Earth observation specifically. I mean, that's what we do. We also, participate in different machine learning conferences. So GTC, you may see us with, NVIDIA. We're in a partnership with them, with Amazon Web Services, and there are other things that I'm not sure I'm supposed to talk about. Probably some announcements about partnerships with Earth observation companies that people will know. Um, so yeah, we try to get our names where, in the right company, known in the right company, and not necessarily plastered all over the place.
Fantastic. So people that want to follow along the news and the updates, I'm assuming LinkedIn, you also have a web page.
Yeah, we have a blog on our webpage that has different things from. So if you're interested more in the industry news aspects of things, then you will be able to see that there, as well as more technical stuff, technical blog posts, and yeah, depending on the kind of content you're looking for, you will find it there.
Fantastic. And you're also on LinkedIn yourself if people want to follow your personal updates.
Yeah, I
Fantastic.
am.
All right. I'll put all the details in the show notes. Well, thanks again for this fascinating introduction to SAR and these interesting applications. And I look forward to hearing again in the future from you.
Thank you very much, Robin. Thank you.